So here we go. I'm recording like that. Okay. Um, and in the WebWorks, they ask you to negate um, natural language propositions of that form. So here's a little useful hint, I should say. So to negate if A then B. Okay, so there, and I think this is one of the exercises. So recall or exercise if you haven't seen it or thought about it. It's in the notes, it's in the slides somewhere. Man, sorry, my handwriting is getting worse and worse. So if A then B is logically equivalent to the following statement. So not A or B. If you think a little bit about this, okay? So again, if A then B is false precisely when A is true and B is false, okay? So it's true all the rest of the time. So think of not A or B when this is possibly false, and you'll see it's exactly the same thing as if A then B. Okay, so not A or B is logically equivalent, so they mean exactly the same thing. Okay, so now if I do the negation of the implication, this obviously will be the same as the negation of not A or B, right? Hopefully you're good with that. And now you have to think about De Morgan's. So this is, here I'm using De Morgan's laws, right? So if I have the negation of an or, it's the and of the negation. So this is the negation of not A and negation of B, right? So this is how I get to the next step, okay? And the negation of the negation, of course, they cancel out. So this is A and not B, okay? This is very helpful for some of the exercises in that WebWorks, okay? So the negation of if A then B is A and not B. It's the same thing, okay? So you can think about this. You can try to go through this by yourselves, but hopefully this makes sense. Okay, so if you're okay, I'm with this. I will switch to um, going back to the slides in chapter 1. Yeah, sorry, I updated the slides. There was a slight little typo on the very last slide. So I had to update that. So let's see. Let's stop this and let's share this like that. Okay, can you see the slides? Yeah. All right. So I'm moving on to sections 1.4, 1.5, and 1.6. I don't know where I'm going to get today. We'll see. But if you recall what we did in 1.1, 1.3, we developed propositional logic, where we saw basically how to combine basic propositions using connectives like or, and not. Okay, and we talked about logical equivalence and such. The thing is that propositional calculus is like a very basic language, but it's too crude. It's too basic for what we actually want to do when we're doing math. Okay, so we'd like to be able to formalize, to write down statements or sentences like the ones that you see on this slide in the example. So if x is bigger than 3 and y is less or equal to z, then z equals to 6. this is something I'd like to be able to play with, to handle. Um, or a statement like there exists a prime number larger than 2 to the power 100, right? This is clearly a proposition in the sense that we define it's either this is true or it's false, right? Whether, I mean, if there is a prime number bigger than 2 power 100, this is true, and if not, it is false, right? Every set is a proper subset of another set. Another proposition. The first one, notice, is not a proposition, by the way. You see there are variables in there. I'm going to talk about each one of these examples in a bit more detail right now. The other one that I got here is for every B and B, there exists an A and A such that f of A equals to B. This is something we actually saw in chapter 2, right? This is the definition of a concept we saw in chapter 2 for a function f to be onto, right? So for every b in, if you have a function from big A to big B, for every b in big B, there's an A in A such that f of A equals to B. That's the definition of f being an onto function, okay? So I want to be able to formalize these things also. So here we go. Let's see what's new here. So I call this first order logic. I will tell you what this means in a few slides later, why it's called first order logic. We'll get to that. So our first example, if x is bigger than 3 and y is less or equal to z, then z equals to 6. Now, this has the form P and Q implies R, right? If P and Q, then R, right? But the thing is that the P and Q here are not propositions, right? So the truth value of these depends on the value of the variables, okay? So these are basically propositional functions. So if you, and the standard name for these is predicates. So if you evaluate, if you plug in values for the variables, what you get is something which is either true or false, okay? So think of x bigger than 3, right? This is a function of one variable, right? And if you plug in a value for x, let's say it's 4 or 7 or -5, what you get is a statement which is either true or false. So this is a function that takes as inputs whatever values of x is taught. I mean, x bigger than 3, maybe it's natural numbers, maybe it's real numbers. We don't know. This has to be specified. But I plug in values, and what do I get as an output? True or false. Okay. So that's what a predicate is. Okay. Now, the only other thing that can happen is that you have more than one variable here. That's the simplest possible example we can think of. It has a single variable, but I could have predicates with, let's say, 2 variables. Think of q of y, z here. So this is y less or equal to z. So to get a truth value for this, I need to plug in a value for y and plug in a value for z. If I do that, I get a statement, true or false, okay? The last one here, x plus y equals to z, then now I need to plug in 3 values for each of x, y, and z. Once I plug in those 3 values, I get a statement which is either true or false, okay? So that's what we call a 3-ary predicate. You can have 2-ary predicates, you can have 14-ary predicates, although we rarely use them, and we won't be using them for examples, obviously, or not too much. But in theory, you can have as many variables as you want, okay? All right, here's another of my examples. There exists a prime number larger than 2 to the power 100, okay? So I can sort of rewrite it using my connectives from last week, right? But I need predicates and I need something new, which is there exists. Okay, so there exists an x such that p of x and L of x. P of x is p is a prime, right? So I plug in a value for x and it says yes if x is a prime, and it says no, false, if x is not a prime. L of x is the predicate x is strictly bigger than 2 power 100. So I plug in a value of x in there. And if x is bigger than 2 to the 200, 2 to the power 100, then this lights up as true, otherwise it's false, okay? But the new thing here is there exists, okay? And that's what we're going to talk about in the next few minutes. So this is a sort of connective, which is a bit different from those that we saw earlier, okay? Next example, every set is a proper subset of another set. So basically the shape of this thing is, for all S, there exists a T such that S is a proper subset of T, okay? Now, S is a proper subset of T. This is a binary predicate. Once I specify what the sets S and T are, this will be either true or false, okay? And there are two variables, so it's a binary predicate. But so there exists, with which I've talked about last slide, and now on top of that there is the for all, okay? So I have for all, there exists, and a binary predicate, okay? So strangely enough, all that I've shown you in these examples, that's all we'll need in the sense of connectives. Okay, so I'll get to that in a few minutes. I'm sorry, maybe it's something in the tea. I don't know. I'm babbling. Bah. Okay. Okay, so let's define properly what a predicate is. So now I want to stress this. In the slides, I don't think I've made that point clear enough. So I will take a few minutes outside the slides, in a few minutes, to really try to make you see how the domain is important. So this is the universe that we are. Think of almost the universal set in a sense, but not quite the same thing. But we have to specify a domain. We'll call it X here, which is a non-empty set. And this is the set about which we are going to talk when we write down sentences or formulas, okay? So the predicates live on this set, okay? So an n-ary predicate on X is a function from the nth power of X to the set true, false, okay? So what does it mean? It means that it takes as input n values from the set X, right? So you can think of it as having n variables. So you're going to plug in n values from that universe or domain X into it, and it'll say something about this set, this domain, and it'll be either true or false, okay? So here are some very basic standard examples. So the first example, and this or at the end means that we could talk about less or equal as being a predicate on n or z or r or q. I mean, there, but here I decided to talk about it on n, the natural numbers. So the predicate q is a two variable predicate, and it is y less or equal to z. Okay, so again, if you plug in two natural numbers for y and z, you get a proposition. You get a statement which is either true or false. Okay. The second one is the sum. Again, we'll be using these two quite a bit. X plus y equals to z. So this is a three-ary predicate. I took it here. I decided that it was on z. It could be n, it could be r, it could be something else. But let's say we talk about it on z. The domain is z. So I take three integers, x, y, and z, plug them in. It's true or false. And I put one which looks more complicated, but just to illustrate that it could be anything, right? T is a four-ary predicate. It has four variables, x, y, z, and r. And the predicate is x squared, y, z cubed, r squared equals to 6. And I decided that it was a predicate on r, okay? And so if you take four real numbers, you plug them in, either this will be true or false. So that's, okay? So hopefully these things sort of makes it, but this is, I mean, this is big. I mean, I used some very, very simple examples, but there are tons of others. Obviously, we can imagine, we can talk about. But to understand basic first order logic, we'll stick to mostly predicates that you are very familiar with, like those first two here, Q and S. Okay. Okay. This slide is scary, and I'm going to skip it. Try to forget it. Okay. I don't want to talk about that. I might come back to it, but don't worry about it. Okay. All right. Examples of predicates. Let's take a few more examples. Let's take our domain to be n. Okay. And I take the predicate q of xy is x equals y plus 3. Okay. So I want to evaluate this predicate. So I plug in 1 and 2. So this will be true or false depending on whether 1 is equal to 2 plus 3. 1 is not equal to 2 plus 3. So this returns false. If I plug in 3, 0, 3 is equal to 0 plus 3. So now it returns true. Okay. Okay, I guess you're getting it. A proposition is actually a zero array predicate. Don't worry about that. I just threw that in there. I don't know. It's true, but you don't need to know that. Okay. So there's no variables in a proposition. It's either true or false without evaluating it at, you need to plug in anything. So that's what it means. Okay, so let's talk about quantifiers. Quantifiers are a sort of logical connective, although it's doesn't connect two things, but it's a way of constructing new propositions. But rather than starting from propositions, it can start from it starts from predicates. Okay. And I say here they are used all the time in mathematics, and I'll talk about this in a few minutes. But I mean, think about any single math result that you have seen in the past 5 years, and if it's written down correctly, there's a pretty good chance that there's a for all or there exists in it. In fact, I'd say about 99.7% of the time, if not 100% of the time, that if it's correctly stated, there's a for all or there exists in it. Okay. So these are the two main quantifiers, for all and there exists, universal and existential quantifiers. We'll see in a few minutes that actually you just need one of them, but it's not a big deal. Okay. So here's our first quantifier, the universal quantifier. What are the ingredients? I start with a unary predicate on my domain or universe X. Okay, so my unary predicate, I'll call it P of X. Okay, again, if I take an element from the set X, plug it in, this will be true or false. Okay, so the universal quantification of P of X is the statement for all X, P of X. Okay, and the notation you see right there, maybe you've seen this for all, this upside down A used before. Some teachers, instructors, professors, mathematicians use this as a shorthand. But if you have never seen it, that is not a problem. Okay, I'm not going to assume you've seen it before, but this is the standard notation for all X, P of X. So this is a proposition. When is it, what does it say? When is it true? It is true, like it says, if P of X is true for all possible values of X in the domain. Okay, hence the universal quantifier. It's upside down A for all. Okay, so this is a proposition. It's something which is true or false. It's not a predicate anymore. So I'm sort of closing the predicate. Okay. Here are a couple more definitions, and then we'll run through some examples. Okay. So again, I fix a domain X. Okay. And I have a unary predicate on X, P of X. And I said for all X, P of X is true if P of X is true for all possible values of X. Okay. So what then does it mean for this statement to be false? For all x, p of x is false means it's not true. P of x is not true for everybody. So it must be false for at least one value, right? Let's say it's called C. So P of C is false for at least one C. There exists a C in X such that P of C is false. Standard name for such an element is a counterexample to for all X P of X, okay? All right, so let's take a look at some small examples. So our domain is R. Again, this is really important. If you're not told what the domain is, it's really very difficult to say anything because depending on the domain, a formula might be interpreted in different ways, okay? So for every x, x plus 1 is strictly bigger than x. Is this true for real numbers? Yeah, right? This is always true. Whatever x is, x plus 1 is always strictly bigger than x. All right, so this is a true statement. It's a true proposition. For every x, x is strictly bigger than 2. Well, no, right? That's not true. Why? Because 1, right? All I need to do to show that this is false is just to find one counterexample, right? I took 1. Okay, you can take 0, -5. There are infinitely many possibilities. You just need 1. Okay, so for all x, x bigger than 2, what does it say? Every real number is bigger than 2. That is not true. Take 1. Okay. For every x, x squared is strictly greater than 0. True or false?
False.
False, because
0 is not greater than 0.
correct. So this is the only counterexample, right? So it's false. Yes, x equals to 0. It is true for all non-zero numbers, but it's false for 0. So the statement is false. For every x, x squared is strictly bigger than 0. This is false. Take x equals to 0. This one is a bit trickier. For every x, x squared is greater or equal to x. You have to think a bit more about this, or you can play with the inequality a little bit, or you can remember that you have to be careful with smallish numbers. But this is false if you take, let's say, x equals to 1/2. If you square 1/2, you're getting closer to 0. So this is false, okay? So you see here that the predicates that I used were all built from inequality sum product, some basic things that you know from the real numbers, right? And I quantified these predicates, okay? Okay, let's now look at the other quantifier, which is the existential quantifier. And like the name says, it says something about existence. So I have once again a unary predicate on some domain X. I call it, let's say, P of X. So the existential quantification of P of X is a proposition. I create a proposition which is denoted, as you see, with this reversed E, E for existence, exists. So it's a flipped E, X, P of X. It's read, there exists an X such that P of X. And you can see just the sentence, right? It's a proposition. Either there exists an X such that P of X or not. I mean, it's either true or false. So it's a proposition. And it is true if P of X is true for at least one value of X, okay? The symbol itself is called the existential quantifier. Okay, so hopefully that makes sense. So now let's think about this a bit more. I'm going to give you some examples. I have a domain X. I have a unary predicate on X. And I said there exists an X, P of X is true if P of X is true for at least one value, little x and big X. So what does it mean that it is false, right? There exists an X, P of X is false means I can never find an element of the set that will make P of X true. In other words, P of X is always false. In other words, for all X, P of X. For all X, not P of X, I should say, sorry. So P of X is false for all possible values of X. Okay, I'll get back to this because you can see that there's a sort of duality when you're negating for all, you get there exist, you negate there exist, you get for all somehow. We'll see that in detail in just a few minutes. So here's an example. I take the domain here to be the real numbers, which you're familiar with, and the statement is there exists an X such that X is bigger than 3. This is obviously true. All I need to do is just provide the X. X equals to 4, for example, right? That's great. There exists an X such that X equals X plus 1. This is not true, right? This is false. We know it's false. We could, I'm not giving you a formal proof. Formal proof. Sorry. Wow. It's Monday. Okay. But you can, you can thanks. So you can, I'm sure you believe this, right? It's clearly this is false, right? But to actually prove it, I have to show that it's X equals X plus 1 is never true for any possible value of X, right? So it's not as easy as the previous one, right? In a sense. Okay. Okay, here's a little shorthand. Oh yeah, I should have told you this just earlier. I'm saying it now. This is important. This is very certainly the part of the course which you'll be the least comfortable with. There's a very good chance this is it. Okay, it's new, it's abstract, it's like so if you're not totally comfortable, it's normal. Okay, it's very normal, and the game, the name of the game is to try to get as comfortable as possible with this. Okay, but I perfectly know how you might feel if you're not comfortable with this. It's okay, it's normal. Okay, my job is to try to make you as comfortable as possible with this. So chapter 1 is a toughie. Okay. Here's a little shorthand that you will often see for all X bigger than 0, P of X. Okay, so we're restricting the domain of the quantifier rather than say for all. I mean, I want to say that P of X is true when X is positive. Okay, so this is a shorthand for the following sentence, and I would really like you to think about this after class, to see that these two things mean the same thing. This is a very important little basic intuition that you should develop. So for every X, if X is positive, then P of X. Okay, so notice that this doesn't say anything about P of X when X is less or equal to 0. It could be true, it could be false, but that's the same thing here, right? So this statement here just says, if X is positive, then P of X is true. Okay, so, and this is exactly what this says. For every X, if X is positive, then P of X is true. So this is the statement. Okay, but this, so this is a shorthand, a way of writing down this longer thing. Okay. Okay, you'll see, you're likely to see this once in a while. Okay, precedence of operators. So the quantify, so we've introduced and or not, right? That connect propositions. And now we've introduced two new things which apply or are applied to predicates, but create propositions. So it means that I can combine them with or, and not, right? So the quantifiers for all and there exists are like the strongest. They have precedence over all the other ones. So if you see this, it means this. So the quantifier applies only to P. That's the first thing that it right? So that's simply a convention to avoid having 17,000 brackets in our expressions, okay? So for all, and there exists, same thing, will have precedence over the other ones. Okay,
It's like for exponents,
yeah.
like it's for the closest thing to it.
Man, I have to think about it. I don't want to answer too quickly because if you write, yes, true, yes, a plus b squared, the squared applies to, yes, absolutely, yes.
Okay, thanks.
Yeah. Okay. Now, what is really amazing is I said most, okay, but actually you could say all of math. We can now route, we can bad day, sorry. Okay. We can write down all of mathematics using the language we have developed. Everything. You can write down everything. For all, there exists negation, or, and the basic predicates, let's say on the real numbers or natural numbers that we've talked about. Exponentiation I didn't talk about, but I'll get to that in a few seconds. But we can write down all of math using this. It's really amazing. Okay, why is it called first order? Because there's also something called second order or higher order logics. First order, as you could see, the quantifiers, they quantify elements of the domain. It is possible also, if you want, to quantify predicates. Things get really nasty. I mean, it just like it's a higher order, higher level of abstraction. So you can start quantifying predicates. That's a much more powerful logic, but it's completely out of the scope of what we're doing here. Okay. So that's what, but just to tell you what the name means, first order logic means our quantifiers quantify only elements of the domain. Okay, so that's all we're allowed to quantify. But that's still, as I said, enough to write down all of math. Okay. Okay. Let's, yeah, here's another reading assignment. I'm shoving so much stuff at you. Yeah, so there's a short section in the book about logic programming. So Prolog, Datalog, SQL. So there are 2 pages in the book. I'm giving you this as a reading assignment. Why? Because there's a couple of problems in the book that deal with this, but I'm going to tell you a secret right now, even though it's recorded, it won't be much of a secret. You'll never see anything on a test about this. Okay, so you do with what you want with this. But if you're like really into programming and you were wondering what we're doing here, what's the connection with programming, this is one very, very direct connection. Okay, so and I'm going to try to make another one. Should I make it now? Yeah, maybe I should. Okay, I'm going to pause the recording because I'm going to do something I shouldn't be doing. Not anyway, not recording. Okay, so nothing happened. Okay. Yeah, actually, you saw Datalog there is you saw in one of those titles, but okay. Okay, logical equivalence. I'm going to try to, I'm going to try to give you, so obviously what I'm trying to do is 2 different things, which is things that you have to do also, is to see like the big picture, to see where all of this, what all of this is about. And also there's the technical aspects where you have to work things out, but they're different things, right? So this is like higher level. Okay, logical equivalence. So when we talked about logical equivalence for the propositional calculus, we said basically it's the same truth table. But now this is way more complicated because we have a universe and predicates. So there's no notion of truth table doesn't really apply here, okay? But what I can say is this: I take two statements, okay, and I can look at them now and fix the domain, fix the predicates, fix everything, and I'm going to get propositions now. And now I can use a truth table, right? Once you've fixed everything, you can use truth tables. But so we'll say that two statements are logically equivalent in this bigger setting, okay, if they have the same truth value, no matter which predicates and domains are substituted in, okay? So here is a baby small example of this. So look at the left-hand side here. It says for all x, open the brackets, p of x and q of x. So what does it mean? It means that p of x and q of x is true for all possible choices of x, okay? On the right-hand side, it says for all x, p of x, and for all y, q of x. So what does that mean? It means p is true for all x, and q is true for all x. Now, if you think about this a few seconds, minutes, however long you want, I'm sure you can convince yourself that these two things mean exactly the same thing, and I don't even have to know what p and q are, right? So this is the key point, is it doesn't matter what the domain is, it doesn't matter what p and q mean, it's just the shape of this thing makes it true or false at the same time, either on the left or on the right, okay? So p of x and q of x will be true for a certain x, means that both are true, right? And if this is true for all x, then p of x has to be true for all x and q of x has to be true for all x, okay? The second one, there exists an x such that p of x or q of x. So what does it mean? It means there's at least one element that will make either p true or q true, okay? And on the right-hand side, actually, this one is maybe slightly trickier. This one on the right says, there exists an x such that p of x, or there exists an x such that q of x, right? So either p is true for at least one x, or q is true for at least one x. If you think, again, a little bit about both of these statements, they mean the same thing. They will be true or false precisely at the same time, whatever choice of domain and interpretation of P or Q you make. These could be wildly different, but doesn't matter which one you take, right? So this will always be true or false at the same time, both sides, okay? So that's what it means to be logically equivalent. I have a couple more examples, and these are really important. So this is, I hinted at that earlier. So the De Morgan's laws for quantifiers. So again, remember De Morgan's, we saw them for union, intersection, and complement. We saw it for or and negation. And this is sort of the same thing again. So if you take any predicate p of x, okay, the negation of for all x p of x is the same thing. It is logically equivalent to there exists an x such that not p of x, okay? So let's think about this. For all x, p of x means p of x is true for all possible x's. You negate this, it means it's not the case that p of x is always true, which means that p of x has to be false at least once, which is exactly what this means, right? There exists some x that will make p of x false. There exists an x such that not p of x is true, okay? Second one, it's like the dual. The negation of there exists an x p of x is the same as saying for all x, not p of x. Again, let's try to think about this. This statement here, there exists an x p of x, means p is true for at least one element. Negation of this means it is not the case that P of X is true for at least one, so it's never true. In other words, it is always false for every X, not P of X, okay? And you can see why this is called De Morgan's, because it flips from there exists to for all when you negate and you put the negation, you flip the order of the negation, right? So this is really fundamental, okay? Hopefully it makes sense, okay? Let's see. Yeah, so this is really important also. Quantifiers do not commute, and this is like really fundamental at many different levels. So here's an example, simplest example I could think of. I took the domain to be the real numbers, and I took the statement for every x, there exists a y such that x plus y equals to 0. And then I flipped those two quantifiers. There exists an x such that for all y, x plus y equals to 0. Okay, now I'd like to explain why one of them is true and the other is false. Okay, so you can't flip these two quantifiers at will. That's bad. Okay, so let's start with the first one. This is for all x, there exists a y such that x plus y equals to 0. So what does it say? It says, give me any real number x, there exists a y such that x plus y is 0. So you take any real number, you can find another number that when you add those two together, you get 0. That is true, right? If you take 5, you add -5. You take minus pi, you add pi. So you just look on the other side of 0, that's the number you're looking for. So you start with any number, you can find another one that will cancel it out. That is true. Okay, this is a property of the real numbers. Now let's flip those two quantifiers and see what it says. What's the meaning? So this says, there exists an x such that for every y, x plus y equals to 0. So this says there is this very strange real number x such that whenever I add whatever I want to it, I always get 0, right? That's certainly not true, right? So there is no x such that whatever I add to it, I'm going to get 0. That doesn't make any sense, right? So how do I prove that this is false? How do I convince myself? Just take this x this supposedly magical x that whatever you add to it, you get 0, and add something that won't give you 0, right? You can do that for every real number, okay? So the order of the quantifiers is really, really important, that you get a completely different meaning if you flip those around, okay? However, if you have the same quantifier repeated, then it makes no difference in which order. And this should make sense, right? If you look at for every x, here my domain is R. If I have for every x, for every y, x plus y squared is x squared plus 2xy plus y squared, or for every y, for every x, blah, 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 same thing. Obviously, these mean exactly the same thing. It says pick any numbers x and y. It doesn't make any difference in which order you pick them. Then this identity will be satisfied. Okay, maybe not, maybe yes. Yeah, in this case, we all know this is true, right? So, and by the way, this is something that it's unfortunate, but when you were doing high school math and maybe calculus, and you were looking at identity, sorry, I hadn't seen your chat. I had another window in front. And now I muted myself. Oh, this is a wonderful, wonderful day. What was I saying? Yes, yeah. So when you were looking at identities, right? So trig identities or identities like this one, right? So what was never written down, but was actually really important is exactly that. This is for every possible values, this holds. Just writing that part doesn't really, it was implied, right? But this is really important for the statement to make any sort of sense. Okay, yes. So okay, so here it just looks more complicated than what it actually is. I just said, I just wrote down what I explained, I illustrated in the previous slide, is that if you have the same quantifier on two different variables, you can put them in any order, it's the same thing. So these are logically equivalent. Phi makes no difference as long as the same thing on both sides, obviously, but you can reorder the quantifiers as you wish. If they are the same, then there's no problem. Okay. All right. Now for the remainder of these slides, the main technical aspect, the main thing that we are going to try to train ourselves to do is to translate from natural language to first order logic and back and forth to understand how this works. Okay. This is not a futile exercise. I can guarantee this 100%. If at some point you reach a level of understanding of this where you can really do it almost automatically, you will have reached another level of consciousness. I promise. It's a step up, not only for math but for anything. Okay. So to practice this, we're going to use some very, very basic predicates, okay? Most of the time. In the book, you might see some other slightly different examples, but I'm going to try to stick to arithmetic. There are many reasons for this. One of the main reasons is this. Reason number one, you're familiar with them. Second reason is we're going to move soon to some number theory, so it will be using these things at that time in chapter 4. Okay, so it means that the domain or basic domain will be usually natural numbers, integers, real numbers. Okay, if it's not specified, it should be clear from the context. On a test, I will always give you very, very, very precisely what the domain is, what the predicates are. Okay. Now, yeah, so the math you saw in the last few years, basically you can write down using the following predicates: x plus y equals to z, x times y equals to z, so sum, product, exponentiation, the ordering of the real numbers, for example, equality, yeah, that's a useful predicate, obviously. And also when we say x is positive, it's a combination of the predicate x less equal to y with constants. We're using some basic constants like 0 and 1 and things like that. Okay, but basically what I'm going to play with are these, but there's tons of other stuff we could be playing with. I mean, the domain could be 0, 1 if we're doing, working on bits and things like that. But here, most of the time, natural numbers, integers, real numbers, and these basic arithmetic predicates. God. Yes. Okay, let's start with an example. I'm asked to write a first order sentence to express the following: the sum of two positive integers is always positive. Now, if you're not told what the predicates you can use are, then this gets a little ambiguous. So I'm telling you the predicates you're allowed to use are the following two. S of xyz is x plus y equals to z, and the predicate p, a single variable, is x is positive. And I'm assuming the domain is z. So I want to write down the sum of two positive integers is always positive. Now, this is written in English. Always is a key word here. So what I mean to say is that if you take any two positive integers, their sum is positive, right? So here is how I wrote it. For every x, for every y, for every z, if p is positive and y is positive and z is the sum of x and y, then z is positive. Okay. Now, you're going to say, oh, but sir, how painful is this? I mean, this is really hard to read compared to in English. Yes, that is true. That is true. And that's why most math papers are not written like that, because nobody would read them, okay? Because it's just too painful. However, it is a very good exercise to translate from one to another. Again, to train your brain to understand precisely what the statements mean. It's very, very important, okay? So there are slight variants which are possible in writing this, okay? But you have to be careful. And my experience in giving this course is that it's very tricky sometimes to convince you that what you may think is correct is not. So I chose an example which is a bit nasty, and I think maybe too nasty to do at this point, but try to think about this, and I'll get back to it tomorrow. And I'm asking you, would this be correct? P of x and P of y implies for every x, for every y, for every z, this implies that. And actually, I took this from an answer on, I mean, it's a variant of an answer on a test that some students gave. And I had to think about how I can explain to them that it's not right. And it's a bit subtle. So, but I want to discuss this to try to clean things up. But I don't want to go into the details of this thing immediately. It's on the next slides, but I'll continue tomorrow. Here, however, I would like to discuss this notion of domain a bit in a bit more detail. So let's stop this share and let's share this instead. Yeah, okay. All right, so domain. Okay, so here's some other examples. I'm going to use the just the equality predicate. Okay, so here's my first example. I take X to be the set 1, 2. Very simple, small set. And I'm going to ask you to consider the following sentence. There exists an X, there exists a Y, there exists a Z, such that not X equals to Y, and not X equals to Z, and not Y equals to Z. What does that sentence say? I'm not asking you if it's true or false. I could have not mentioned the domain at this point specifically, but anybody who wants to say in English, what does this sentence says?
Well, I guess that would mean that there exists 3 numbers such that they're all different from each other.
Yes, not necessarily numbers, but elements. Yes, that's exactly what this says. This formula precisely says the domain contains 3 different elements, right? So it says the domain contains at least 3 distinct elements. Right? So there exists X, there exists Y, there exists Z, such that X is not equal to Y, and X is not equal to Z and Y is not equal to Z. So they are different, right? So is this sentence true or false in that specific domain? It is false. Okay, so let's call it phi. Okay, so phi is false in X equals 1, 2, but it is true in, let's say, the natural numbers or R, or a set at least with 3 elements, any set with, right? Okay, so I wanted to emphasize the fact that the domain is really important, how you interpret, and I didn't use any very, very sophisticated predicates. I just use equality predicate, which is usually a given. If you're doing logic without equality, it's hard to, some things are really hard to say, okay? So I have a sentence here, a formula or a sentence that says the domain contains at least 3 different elements. So in a domain with 2 elements or 1 element, it's not true, and you can probably figure out how to write a sentence that would say there are at least 175,000 different elements at least in the domain, right? What is not so obvious is how you would write there are infinitely many elements in a domain. You can try to think about that, but that's a much harder question. Okay, so that's something I wanted to add here, I think I'm going to stop here because yeah, unless yeah, I'm gonna stop here. I mean, other than questions and so to recap, I'll continue the slides tomorrow. I will post these also, although there are just a couple of extra slides, but I'll just post those. And WebWorks, you have one closing, although most of you have done it, but it's just 3 little questions. There's another one that's open just this week, 4 questions, very simple. And then there's like a bigger one that you have a couple of weeks to do. Any questions, comments I can hopefully answer without getting a cramp? If you prefer asking your questions in a private, I will stick around. I'll just stop the recording and you can